going to propose a structure using the molecular formula, infrared, carbon-13, and the proton spectra to help us. Since we were given the molecular formula, let's start with that. We can find the degree of unsaturation using the formulas 2 times C plus 2 plus N minus H plus S all over 2. C is carbon, N is nitrogen, H is hydrogen, and X is halogens like fluorine, chlorine, bromine, iodine. Let's plug in what we have. 2 times 4 plus 2 plus 0 minus 6 plus 0 over 2 gives us 2 degrees of unsaturation. The degree of unsaturation tells us that the molecule could possibly have 2 double bonds, 1 ring and 1 double bond, 2 rings, or 1 triple bond. We won't know what it is until we draw out all the structures, but then again we would need another method to determine which one it is the correct one. So to be more time efficient, let's look at the other information given. Here we have the infrared spectrum. The peak that tells us the most information is around 1780 cm1. It's a carbonyl carbon, and that is a carbon double bonded to an oxygen. This helps us eliminate the possibility of it being a triple bond or having 2 rings. It can also help us narrow down our list of functional groups to ketones, aldehyde, esters, carboxylic acid, amides, or thioesters. It can't be a thioester because there is no sulfur, it can't be an amide because there is no nitrogen, and it can't be a carboxylic acid because it does not have an OH group. The OH group or hydroxyl group usually falls between 3200 to 3400 cm1. So let's fill out our chart. The carbonyl carbon falls around 1780 cm1. The sp3 carbons usually show up around 2900. The sp2 carbons usually show up around 3000 cm1s. Peaks in the fingerprint region below 1500 cm1 can be hard to read, but there are some peaks there. From the molecular formula, we know that there is another CO bond somewhere, and that bond usually falls between 1000 to 1300 cm1. So the big peak at 1190 cm1 could possibly be our CO stretch. Now that we narrowed it down to ketones, aldehyde, esters, let's look at the carbon-13 spectrum to see if it can help us further. First thing I notice is that there is 4 peaks, and based on our molecular formula, I know that there's 4 carbons. This tells me that there is no symmetry in the molecule. From the IR spectrum, I know that we have a carbonyl carbon that typically falls between 180 to 220 parts per million. Carbonyl carbons usually appear more downfield because 1. The carbon is sp2 hybridized, and 2. The electronegative oxygen pulls electron density away from the carbon, de-shielding it and causing the signal to shift to a higher parts per million. Ketones and aldehyde carbonyl carbons usually fall between 200 to 220 parts per million. Here, the furthest downfield signal is 180 parts per million. This suggests that the molecule is not an aldehyde or a ketone. Now that we eliminated ketones and aldehyde, let's continue and fill out our chart to see if we can confirm if it's an ester. From our IR spectrum, we know that the carbonyl carbon is present, and our carbonyl carbon signal is around 180. The next shift we see is around 68. This signal suggests that it's our CO bond. The signal usually appears between 50 to 80. The oxygen is more electronegative than the carbon, so it pulls electron density away from the carbon, making it less shielded. The third and fourth signal that we see is around 20 and 30 parts per million. This is mostly likely our C bonds. These bonds generally appear below 40 parts per million. We now know that it's an ester. Let's use the proton spectrum to see if we can confirm it and give us the general idea of how it should look. We see a total of 3 different hydrogen environments in the spectrum with an integration ratio of 2 to 2. For each environment, this means that each group of protons has 2 hydrogens. The signal at 4.3 parts per million shows 3 lines, which is called a triplet. The triplet indicates that the proton has 2 neighboring hydrogens. This suggests that the CH2 group is next to another CH2 group. The next signal is around 2.3 parts per million. It's also a triplet, so it's another CH2 group next to another CH2 group. And the last signal is around 2.1 parts per million, and that has 5 lines, so we call it a quintet. This indicates that this proton has 4 neighboring hydrogens, most likely in between the 2 CH2 groups. Now that we have all that information, let's look at the possible structures. For the structure on the left, we have 2 degrees of saturation, and here we only used 1, so it's not correct. Also, the integration and the multiplicity does not match the spectrum or the table we have created. The structure on the right, we use both degrees of saturation in 2 double bonds, but the ratio and integration is still not right. Also, there's only one spot for the second double bond. There's only one spot that the second double bond can go. Oxygen can only have 2 bonds. This confirms that this molecule does not have 2 double bonds, but 1 double bond and 1 ring. Thus, this is the molecule. It has 4 carbons, it has 3 different proton environments, and its multiplicity makes sense. The CH2 directly across from the oxygen has 2 hydrogen neighbors. The CH2 next to the oxygen also has 2 hydrogen neighbors, and the CH2 in between the two CH2s have a total of 4 hydrogen neighbors. Thus, this is our molecule or structure. I'm not sure how they got the name because I would have named it differently. We know that it has 4 carbons, it's an ester, and it's in a ring. So I would have named it cyclobutanoate or cyclobutyl, but that is wrong. Online it says a cycloester is a subgroup of lactone, hence the name gamma-butyrolactone. And that's it.